Yes.
Okay. Sorry, 1 second. Okay, all set.
All right. Thank you, Dr. Sultan. So we are Team Sustainable Braking. We are designing a autonomous magnetic braking system that will function with object detection.
Here is a brief outline of our presentation. I won't go over everything here. This will be explained further in the PowerPoint.
So starting with me, my name is Mike Rodopoulos. I'm a computer engineering major interested in cybersecurity. I will be assisting in software development and employment, applying system calculations, and doing the sensor deployment.
Hi, my name is Owen Hafner. I'm an electrical engineer, interested in RF communications, and I am the team leader for this project. My role is to design the hardware aspect of this, and along with the circuitry involved.
My name is Joseph Venturini. I'm a computer engineering major with a concentration in cybersecurity, and my role for this project will be developing and testing the software.
Yeah, I'm Ian Healy. I'm interested in system administration. My role is to develop hardware and bridge the software and the hardware when that comes next semester.
So our motivation for the project relies on some current issues with current braking systems today. So most automobiles on the road use disc braking, and those brakes are prone to wear. They create large amounts of heat, and they require a lot of maintenance. So a more sustainable disc brake system is in the market. However, it is not a reasonable solution because they are far too expensive for the average consumer to implement. So vehicles on the road today need a non-degrading and more effective solution to braking, and there are several benefits to reducing pad braking or physical braking, such as eliminating regular replacement and maintenance on braking systems. And based on interviews with customers, we learned that they would like to have a system that requires less maintenance, and it would prove that they would save money in the long run by not having to conduct regular replacement maintenance, and things of that nature.
So for our project selection, at first we discussed magnetic clamping. This would be where we use electromagnetics to provide braking force using friction. That still it improves efficiency, but it still has the issue of having physical wear. Next, we discussed a fully electromagnetic braking system. This does not provide enough force without running into issues of heat, and ultimately the device would not last very long. So the project summary, we decided to use a magnetic force using neodymium magnets placed in close proximity of an iron disc. The servo will be used to move the magnet into place. Object detection will be done using a LiDAR sensor, and it will detect distance and give us information to then provide braking.
So the reason, again, why we chose this problem is much more effective or cost effective for consumers. They don't have to be spending so much money. On average, on a 200K lifespan of a car vehicle, consumers will spend on average $4,800 on brake pad and rotor replacements. That's something we want to cut out. And if our solution does have higher initial costs, it will be offset by basically no maintenance cost. And it provides a much more green solution to braking.
So for our market and competition, brake parts can be widely sourced from car manufacturers and independent auto shops. And electric vehicles today utilize a regenerative hydraulic hybrid braking system, which, as you can see on the chart on the right, takes up a lower braking torque. And regenerative braking only applies a small amount of brake force itself. And hydraulic brake system still accounts for a majority of the braking torque, as you can see on the chart on the right. It takes up a lot of the braking torque, while regenerative braking is a little bit lower on the scale.
So there haven't been any previous examples of fully magnetic braking in commercial vehicles. We plan to change that. But in trains, Japan's Shinkansen high-speed railroad has some of the best safety records on the planet. It does run on electromagnetic braking. Over the last 50 years, there hasn't been a single fatality or injury. So it just proves how safe electromagnetic braking can be if we can fully implement it in cars.
For our needs identification, as you can see, the safety is split into reliability and performance. We want the project to brake reliably and consistently. And as for the repairs and the maintenance, they shouldn't be too much of an issue when the initial cost is higher than it. And as for the chart on the right, is basically how we would go about designing the project. We would determine the requirements and then create each component based on the requirements, where we would do the same for the software, and each would combine to finish the project.
Here we have the ranking of the categories, considering safety, repair costs, and initial cost, giving us the overall score and weight of each category.
So if it wasn't already apparent in the previous two figures where safety had the biggest number in the charts, safety is absolutely the number one priority, especially in any braking system, and should be in any project. In the case of braking, we don't want the system to brake too fast, like the way you stop short. If the initial cost is higher than standard braking, then it should have much lower replacement and repair costs, as I said previously. Additionally, if the additional cost is higher, then there should be improvements in the braking performance with the lower replacement and repair costs.
All right, so some of the requirements for engineering the system. So based on a study, we found that the average stopping distance of the vehicle from 60 miles per hour is about 132 feet. That is in normal conditions using standard coefficient of friction. So this would result in an average deceleration of 29.3 feet, or about 20 miles an hour. And so we want our system to have about a max acceleration of 32 feet per second, or which would relate to 22 miles an hour. And we also would like it to have fast reaction time when detecting an object to have maximum safety and maximum performance.
Here's the trade-off matrix. So we have the arrows indicating how strong the correlation is, whether it's positive or negative. So as we can see, safety and braking force, they're both heavily positive correlation, whereas the performance and the cost have a strong negative correlation.
Here's some of the theory that we used in our requirement engineering section. So using physics, we can calculate the distance needed to decelerate or to fully brake an object. That would be through the initial velocity over 2 times the acceleration. But that would not be a sufficient equation if we were, let's say, on a hill or some kind of an angled slope. So in that case, we need to account for gravity, and you can see the second equation. So now you're taking into account gravity, you're taking into account the road grade, and you're taking into account the coefficient of friction between the tires and the roads, which is variant depending on conditions. And then also we can use magnetic equations to solve for the attraction force between are neodymium magnets and the pure ion disk, which would be A equals C over D squared. A would resemble the attraction force. C is the coupling constant between the neodymium and iron disk. And then D squared would represent the distance between that magnet and the disk. So our approach, we first determine the required force necessary to meet our engineering requirements. And then from there, we are able to design the magnetic system and electrical components, which would be needed to operate at desired parameters. And then lastly, we can develop software needed to control the servo, to run our object detection system. And we can bridge that together with the hardware in order to have a complete system. And we would test our system, calibrate, take measurements, and solve any issues that might arise during testing.
This is our level 0 functional decomposition diagram. This is pretty much just a shorter and vaguer version of a diagram that we're about to show you on the next slide. This is our level 1, which I am able to explain because there's a lot more going in for it. Basically, we're going to be using a LiDAR sensor for object detection. The output of the sensor is going to be put into an Arduino Uno for distance calculations, where as the object detection there, once it detects the distance between the device and the object, it will send an output to the servo if it gets close enough, and the servo will deploy the electromagnet to the iron disk, and the motor will be cut off. So the car or vehicle we will create will stop, and they are all powered by a 12.2 volt lithium polymer battery that powers both the Uno and the servo.
So here we just have a little CAD design I threw up in Inventor. It just has a general outline of what our car should look like as a completed project.
On this next slide, we have the system architecture, basically just showing the overall block diagram of what's going on here, very similar to the last slides, involving the PWM circuit, as we'll see in the next slide with the electrical schematic, the motor driving the axle, so on and so forth. So now the hardware design, we have the sensor. You can see the input. It's taking power from the Arduino Uno. Arduino Uno is getting power from a voltage regulated power source. The main battery is powering the motor, which is modulated by a pulse width modulation circuit, which is also controlled by the Arduino Uno, taking input from the sensor. This is the picture of the current design. We have the front half of the car built right here. It's involving the motor, the servo with the magnetic plate, moving into position with the iron disc. This is the battery, the lithium polymer, Arduino Uno, and the PWM circuit.
So here is just a snippet of some sensor code that we will use for testing during the winter break and next semester. So we have not received our sensor yet. As we said earlier, it is a TF Mini S LiDAR sensor. It provides good range, high refresh rate, and should provide good performance for our system. So the following flowchart just shows the implementation of how we will test the sensor using some built-in Arduino libraries.
So after the sensor code, we decided to show the servo code.
Sorry, 1 second. I'm back on this slide, of course. Okay.
So after showing the sensor code, we decided to show some servo applications. Basically, how the servo code works is that it uses a custom header, as you can see by the servo.h, that allow it to make use of the 3 wires on the servo, which are the ground, the signal, and the power. All of these wires are going to be incorporated with the Arduino in some way. and they allow for general movement and rotation of the servo. Using this, the functions, it will allow us to integrate normal functions with the Arduino, that such as digital write. For something like an LED, you could write low or high to it to turn it on or off respectively. However, with the servo's case, it'll just disconnect the servo from power or reconnect the servo from power.
So quickly, we just have some risk analysis, safety. We've talked about that before. It's one of our top priorities, along with component testing and reliability, making sure everything works fine and it's within spec, because you don't want someone breaking when they're not supposed to, or not breaking when they need to. Here we just have some of our iterations. We had initial designs of the base plate that were changed and CAD designs that were changed in progress. We're having friction from gears, so we plan to implement a pulley system. And we also plan to install a pure iron disc upon shipment. It's shipping right now, but when that comes in, we'll be able to add that.
So for our testing parameters, we will plan to do unit tests to ensure the functionality of each unit before integration, and it involves testing the servo sensor and the braking system. For integration tests, we ensure the functionality of all of them together, and it ensures that each unit should interact properly with others. For acceptance, those tests are when we will test the fully designed system with both halves of the vehicle, and we will test the acceptance of the engineering and design requirements.
So here we just have a little testing that we have going on that we've done. There are just the dates and the tests we did with corrective actions with the problems we faced when testing.
So on the test video, you have to exit the viewer, go into Google Slides, go into Google Drive. Okay, so here we have a video of the motor being driven by the power supply. It's set to 12 volts initially, and the magnet is then actuated. You can see that the current being drawn is increased. Then moving forward, so I de-engage the magnet, reduce the voltage down to 6 volts. And then re-engage the magnet. You can see the current goes from 0.1 amps to about 0.34. So we're looking to, in the future, smooth out that that motion with the gears. Next slide.
We just have a short timeline for our spring semester and future plans. I'm not going to go into detail. And here's our bill of materials. We've bought all the parts already, so our cost is under budget, and we plan to stay within the budget allocated.
So for the future work, we are planning on finding a smoother way of using the motor to drive the axle, so it could possibly be a belt-driven system. We will have to use the sensor, get that to work properly to get us accurate distance measurements. We have to then combine the code with the hardware to move the servo, provide the proper amount of braking force, and then calibrate the device.
So we just have some codes and standards, so I'll make this quick. Currently, all braking systems have to be connected mechanically to the wheels and the pedal. We need to research to see if a planted servo can function as a mechanical connection. Our battery connector is an XT60, which means you can deliver max current at 60 amps. That's a standard. All battery connectors use that. And also we have some of our testing at the bottom there. It's some codes that need to go through all braking systems must do this. They have specified speeds you need to brake in effectiveness tests, and we're going to test those and see how we compare to brakes on the market today.
Just a couple notes about ethics. So this is a green, eco-friendly solution. So we're saving materials, reducing pollution. So this is good for the general consumers. And then a few issues that need to be addressed and determined will be for backup solution if the battery were to fail, if the magnet warps under high torque, and then we need to account for different road coefficients.
Okay, and our last slide, real quick, complex engineering under a multidisciplinary project. We're electrical computer engineers. We have mechanical engineering knowledge with CAD designs and working with motors. We also have computer science knowledge with coding with the servo and the object detection with the sensor.
And those are just our references.
Any questions? Thank you. Thank you, everyone. Thanks for the presentation. And without further delay,